Dalton's law of partial pressure says that the total pressure of a gaseous mixture is equal to the sum of the partial pressures. Now, the partial pressures are the pressures that each gas would exert if it were by itself in the container. A few other equations that are going to relate to Dalton's law of partial pressure are the total moles of gas in a mixture is equal to simply the sum of the moles of one gas plus another gas plus another gas. So that's more of an idea than an equation. As is the mole fraction of a gas in a mixture. The mole fraction is the number of moles of a particular gas divided by the total number of moles of all the gases together. So let's try a problem. Find the total pressure exerted by 38.0 grams of carbon monoxide and 38.0 grams of hydrogen in a 6-liter container at 25 degrees Celsius. Let's think about this, and here's our battle plan. We're first going to find the total number of moles, and then we're going to use the ideal gas law based on that total number of moles to find the total pressure. So the number of moles of carbon monoxide is going to be found by taking 38 grams. Carbon monoxide, of course, has a formula of CO, so its molar mass is 28. 38 grams of carbon monoxide is 1.357 moles of carbon monoxide. Let's do the same thing for the hydrogen. We have 38 grams of hydrogen, but the molar mass of hydrogen is only 2. 38 divided by 2 is 19 moles of hydrogen. So although the masses of the two substances are the same, there are many, many more moles of hydrogen. If we add those up, we get the total number of moles of gas in the mixture. So let's use the ideal gas law and calculate the total pressure. N is 20.357. It doesn't specify in the problem what the unit should be for pressure. Therefore, that gives us a little freedom to choose the value of R however we wish. So I'm going to use this one, 8.314, which means that our pressure is going to come out in kilopascals. The temperature needs to be converted into Kelvin, so I haven't shown that step, but I'm just mentioning it. 25 degrees Celsius turns into about 298 Kelvin, and there's our volume in the correct unit of liters. 8,410 kilopascals. With reference to the previous problem, what is the partial pressure exerted by each gas? And the main idea here is that the ratio of the partial pressures is the same as the mole ratio. In other words, it's the number of moles of a gas that are going to determine its partial pressure. The mass of the gas is irrelevant. The partial pressure, that is the pressure that the carbon monoxide exerts, is simply the fraction of moles that are carbon monoxide, which is 1.357 moles of carbon monoxide over a total in the mixture of 20.357, multiplied by that total pressure, 560 kilopascals. That quantity right there is the mole fraction. You could make it a decimal, but I'm just pointing out that if you calculated that, that would be the mole fraction of carbon monoxide. We're going to do the same thing with the hydrogen. 19 moles of hydrogen divided by a total number of moles in the mixture of 20.357 multiplied by the total pressure, 7850 kilopascals. That's pretty amazing that the same mass of two different gases can exert vastly different pressures because the pressures depend not on the mass but on the number of moles. Let's summarize Dalton's law of partial pressure 1. A partial pressure is the pressure exerted by only one gas in a mixture of gases. Dalton's law says that the total pressure exerted by the mixture is simply the sum of the components' partial pressures. 2. The total moles in a gaseous mixture is the sum of the moles of the component gases. Obviously. This means that, in any mixture, the ratio N to P for any gas is a constant. That is, the proportion of moles determines the proportion of the pressure for a given component, and the total moles determines the total pressure.